Welcome to this video on the logistic equation, which is shown at the bottom of the page here. In this video, we're going to perform a phase plot analysis in order to determine the qualitative nature of the solutions of the logistic equation. We're going to be looking at the logistic equation where R has been specified to be equal to 3/2, and K, the carrying capacity, is specified to be 4,000. And let's just think of N as the number of individuals in a population as a function of time, where time is measured in days. So we start our qualitative analysis by making a graph of dn dt as a function of n. And this may look a little bit odd at first, but if we rewrote this equation as y is equal to 3/2 times x times 1 minus x over 4,000, and I asked you what is the graph of that equation, I think you would all say, oh, well, that's just a parabola that is opening down. So this here is a parabola opening down with intercepts at 0 and 4,000. So with intercepts x equal to 0 and 4,000. So if we translate that into our current symbols, we have dn dt takes the role of y and n takes the role of n, and so we just simply end up with that parabola. We end up with the parabola that opens down and has x intercepts, or in this particular case n intercepts, at 4,000 and at 0. Okay? That's a great start. All right, now let's go to the next page where I have the plot drawn already, but with a little bit more space. And now we're going to analyze the sign of dn dt. So certainly when n is less than 0, we can actually just discard that, because in the context of a population, n being less than 0 means that we have a negative number of individuals. That is nonsensical. So this is not of interest in the context of a population. It's not of interest in terms of a population model. And then let's take a look at the case where n is between 0 and 4,000. In that particular case, we see that the graph of the right-hand side of the differential equation is positive. And so that says that dn dt is positive. And that implies, if dn dt is positive, that implies that n of t increases. So it increases, and let's indicate that by an arrow on the n-axis that is pointing to the right. That says that n is increasing. So, so this is indicated by arrows pointing to the right on the n-axis. Okay, now let's take a look at n being greater than 4,000. So for n being greater than 4,000, we see that the red curve dips below the n-axis. With other words, dn dt is less than 0. That implies that n of t decreases. And we can indicate that with left pointing arrows on the n-axis. So this is indicated by left pointing arrows on the n-axis. Okay. Now we've skipped a few points. In particular, if n is exactly equal to 0, then, well, we're sitting at an n-intercept, and so we know that the n dt is equal to 0. And that says, or that implies, that n does not change. It remains 0. If it ever is 0, it remains 0. And so that actually says that n equal to 0 is an equilibrium. Okay, and similarly, if n is equal to 4,000, we have exactly the same thing. The n dt is equal to 0, and so n equals to 4,000 also is an equilibrium. Okay, and then the last observation that we want to make is that the larger the value of the n dt, or really the magnitude, the larger the magnitude of the n dt, the faster n changes. Okay, and in terms of the slope of n of t, it implies that it's the steeper the slope of n of t. Okay, so on the right hand side we have a lot of information about what the solution n of t is doing, where it's increasing, where it's decreasing, whether it's increasing just a little bit or whether it's increasing a lot. And so it certainly, in terms of the graph on the left hand side, the n dt is the largest right in the middle between the two equilibria, between 0 and 4,000. So right at 2,000, the slope would be the largest. So I'm going to put 3 arrows there saying that n of t changes a lot over there. All right, that's a lot of information. Now we're going to put it all together and determine the graph of n of t for different initial conditions. Okay, so I have our familiar graph on the left for dn dt versus n, and now I'm going to use that information to infer the solutions of for the differential equation, so the graphs of n of t. So let me start with 0 and 4,000. So when n is equal to 0, we're at an equilibrium. And so my initial condition 1, if it's equal to 0, then I'm going to stay 0. Okay, and similarly, if n is ever equal to 4,000, then it stays at 4,000. Okay, and so that was the second initial condition. This one here is number 2. Let's start with an initial condition, say, right over there. A little bit larger than 0, but not above 2,000. So I'm going to start, say, over here. Oops, that's also at 2. I should really call that, let's call that 3. So 3, this is 3 right here. Well, now what's going to happen? And initially, my dn dt is positive, but it's not a lot, very positive. So I've got an increasing function. N increases at this point, but it has a relatively shallow slope. But as n increases with these arrows that I have over here, and so I'm putting various arrows. The more arrows I have bunched together, the larger the slope is what I'm trying to say over there. And so it's the same thing over here. And so the closer you get to the equilibrium, the shallower the slope is going to be. And so the maximum slope is reached at 2,000. So my slope is increasing, increasing, increasing. My maximum slope is reached at 2,000, and now the slope is starting to become shallower. And so there's my solution, and as I get closer and closer to 4,000, I get shallower and shallower and shallower. Let's take another initial condition. Let's start between 2,000 and 4,000. So let me start, say, over here. So that's initial condition number 4. So let's put 4 over here. What's going to happen? Well, I'm again increasing, but as my n increases, I get shallower and shallower. The slope becomes closer and closer to 0. So that's the solution with initial condition number 4. And then last, let's also take an initial condition above 4,000. And so let's take initial condition number 5. We'll put that on the n-axis over here. Now dn dt is negative, and so I'm going to be decreasing, or n is going to be decreasing. And at first it's increasing sharply, and then the closer and closer you get to 4,000, the shallower the slope becomes. Okay, so there it is. There is a picture of all of the types of solutions that you can get for the logistic equation.